Hi there again. Yes, so we are coming lower in frequencies, so now we are back in radio, but not the standard radio that you're used to. And with the standard radio, I mean like L-band or low frequency observations, which we usually use for observing pulsars or FRBs, and it makes sense, right? The spectral index, pulsars, and FRBs are very bright there, so it's like our comfort zone. So I would like to present you what will happen if we observe promising sources at higher frequencies at the ALMA band. So I'm working now there in the science department. This work. And I mean, it was a long title, but the main question is like, can we detect pulsars and FRBs with ALMA? And in case you're not very familiar with ALMA, it is a radio telescope there. But the idea is that it's located in Chile, in the Atacama Desert at 5,000 meters of altitude. And there is a good reason for that. The Atacama Desert is the driest one in the world. And the altitude is because when you go to these higher frequencies, the atmosphere matters. So you want to be there. So ALMA is roughly 66 antennas. Some of them, most of them are 12-meter dish. The other ones are a bit smaller, 7 meters. But the key point is that ALMA is an interferometer, meaning that most of the observations it does is spectroscopy or imaging. So unfortunately, not really pulsars. And from the observation frequency, it can go from 35 gigahertz, this is the lower band, the lowest band, and up to 95 gigahertz, so basically millimeter and submillimeter. The lower part of the band, that's a new capability. It started last year, and this year it's in full mode with polarization and all the capabilities that we will need. And I will explain later why. So I said ALMA in principle was not made for pulsars, but it doesn't mean that we cannot use it for observing pulsars. And for this, we are sort of connected with VLBI. And although it's a very different observing mode, the main reason is that when you do global VLBI, so each telescope that you use in your network is a data point or a time series. So in this case, when ALMA joins this global VLBI, so GMVA or even Horizon telescope, all the antennas of ALMA are phased to create one single equivalent dish antenna of roughly 80 meters. So when you consider this 80-meter dish in the millimeter range, I mean, it's top, right? There is nothing that can compete in that frequency range. So this part is the standard VLBI, so we use the ALMA correlator, but then we need to pass it to a different processing mode because this is not a standard. And then we will pass this VLBI data at a VLBI center, and we will convert it, channelize, and make something more familiar to us, which is a search file. Can be PSR feeds, can be filter bank, but this is what we can get nowadays. Here there are some properties of this data that we can obtain with ALMA. So a resolution of 8 microseconds, we can go even lower to 2 microseconds, full stop capability with band 3 and band 1, which means 35 gigahertz up to 100 gigahertz. So there is a huge frequency range there. And with a 2 gigahertz bandwidth and some sensitivity there, which is quite good, because it's equivalent to a large telescope. But this is a small community. Not many people are doing a high-frequency radio observation of these radio transients. So my idea was, okay, let's characterize this observing mode so more people can join and observe. For instance, if you have a promising pulsar that is in a dense region, like a supernova remnant close to the black hole, then you could go there because with this frequency range, we are not really affected by scattering, right? So you can probe deeper into denser regions. So if you got some promising pulsars in supernova remnants, perhaps we can give it a try. So how do I characterize this mode? By using archival data, because I need something to afterwards go to ALMA and say this works. And we used EHT data that ALMA recorded back in 2017. And why do we use this data? Well, first of all, because there is a magnetar that is located close to the black hole. The name of the magnetar will come later, but it's known as the galactic center magnetar. And for practical purposes, the black hole is here, and 3 arcseconds away, it's the magnetar. The good thing about this is that we get the data for free whenever someone wants to observe the galactic center magnetar in phased ALMA mode, so mostly VLBI. So we did this. We are reprocessing the EHT data, the part of ALMA. Our data is unfortunately not that glamorous as this here, and it looks more like a time series. This is what we are used to, right? And we started this as a summer internship of Josefina when she joined me at ALMA. And we have some detections of the galactic center magnetar in single pulses. Single pulses is the pulse that comes from one rotation. This is one example of it at 86 gigahertz. So you can see significantly bright, and we have linear polarization, circular polarization, and like this we have at least other 7 single pulses. So what we did was to process this as if we were analyzing fast radio bursts, because this is, we also want to do the estimation, like can we really observe FRBs, and is it realistic to try to do this? So with all the pulses, we still haven't processed all the data, so perhaps we have even more than 7 pulses. We calculated the cumulative energy distribution, as we would usually do for fast radio bursts, and then we obtained a gamma value of minus 2.0. I mean, these values, this type of analysis was not done before for this magnetar, nor at these frequencies. And we do this, we extrapolate, okay, if we observe at a bit lower frequencies, which is now possible with Band-1, we expect to detect several more pulses. Now, why do we want more pulses? Well, because if I observe at Band-1, it's a way to start learning about the emission properties of the sources. We know from radio that the emission is coherent, but at some point it stops being coherent. And this will be seen, and it's probably within the ALMA band. So we start pushing like higher and higher, and then we see up to which point we can detect the coherent emission of pulsars, magnetars, and so on. And so we did this, and this is work in progress now. Josefina is publishing this work. And for doing this, it's not a standard search. So it is Presto-based as well, but there are several things that we need to take into account when we go to higher frequencies. First of all, it is a benefit that we don't have dispersion, right? We can probe deeper into denser areas, but it's also a problem, because if you do pulsar search, you know that DM, it's our friend in the sense that it allows us to check whether a source is real or not, or it's a radio frequency interference. If we go to ALMA, DM 1800, which is the DM of the source, is the same as DM0, and yeah, sure, it makes sense. The dispersive delay is 10 microseconds, so we don't see it. But that makes it bad when we're doing the search. And this is why we do need polarization properties for our observations. Otherwise, even if it's true that we don't have radio frequency interference at these higher frequencies, there are some artifacts that come because of the phasing system of ALMA. So in this case, with polarization property, we can say, okay, this is most likely a real signal. And if we know the pulsar as well, we can use the ephemeris maybe to see where the pulse arrived. And as well, the study was done with the tools that Pranav here, which is also part of the log, had developed for his study of fast radio bursts. And we were doing this in single pulses, but Kuo Liu published also processed this data, and in this case, he did it in integrated pulse profile. So he took the 2.5 hours of observations, he folded with the time with the ephemeris, and you can see that in integrated pulse profile, the source is very bright as well, polarization properties. He also had really nice constraint on the geometry, like the inclination axis and some other stuff. Because at higher frequency, scattering is not a problem, and depolarization is less of a problem as well. So, answering the question, we characterize with this data set fairly well band 3. We are extrapolating some information for the sensitivity on band 1. What we estimated is at band 3 we should be able to see something like 100 pulsars. You can see them there. The ones that are above should be detectable. Some of them are well-known sources like the Vela pulsar, but the Vela pulsar probably you can detect even with a mobile phone. And if you go to band 1, lower frequencies, spectral index plays the role. And then we should be able to detect something like 200. That's a large population of pulsars right there. Now, if perhaps you can better visualize this in sky view, this is the part of ALMA that is the part of the sky that is not visible to ALMA, so above 47 degrees in declination. In purple are all the pulsars that are visible to it. And in orange are the FRBs, so many of the repeating FRBs are not visible, but many of the very actively ones are visible first. Now, there are some caveats. This is still an early observation mode. There are many things that we are sorting out. And especially if you're planning to put a proposal for ALMA, there are some things that you should keep in mind. First of all, ALMA does not guarantee the number of antennas. Okay, so when you do your calculation, do not put the maximum number of antennas. Do not put 50. Most of the time, we do not observe with this number. It's more like 40 something. And you see that the sensitivity the sensitivity increases when we have more number of antennas, but sometimes, I don't know, the array is 16 kilometers in size, and part of the weather is a bit bad, so some antennas will go offline, and so on. Another thing is that the data is recorded in bits, so we don't get, as we will get in a single dish observation, like one time series, we get like pieces, and it's not continuous, because ALMA goes on source, off source, on source, off source, for calibration purposes. And also this means that when you calculate the overhead, you need a 3 times factor. Usually it's 10 or 20% when we observe, for instance, with FRBs. So if you need to observe your source 2 hours, then you need to request 6 hours, which is still not a large number for ALMA. Most people will request 20 or 30 hours. And the ALMA the phased window is restricted basically to the EHT and GMBA running every year. And as well, the data is quite heavy because you get the data for each antenna and then you take it to a VLBI center and then it's correlated to get your PSR feeds. But we are working on it. And in fact, for instance, with QO, we are working on formatting the data, so when people observe, they can just get one single file, search file, that afterwards they can do the folding or the search or whatever they want to do. And with JohnCode, we are working in the software for having the smooth processing of the data. And what we all have in common is that we all met here at Max Planck. So thank you very much.
Despite it's very weird to have my face on when sharing your section, please, if you have any question, please.
No, it doesn't work like that. So the, I mean, for the you mean for the phasing of the ALMA? Ah, no, you mean for saving some time. Not really. So the thing is that the weather is also quite local. So for instance, sometimes most of the antennas that are in the compact part of the array have one weather and the one outside has a different one. So you do need to consider all of them. And from the observational point of view, it means that you need to have 2 arrays, which you can make, but then when you need to integrate them for boosting the sensitivity, you will waste some time going there. So at the end, you will not save any time. Of the image, it should be something like milliseconds.
For imaging?
I think in principle they can push it. They usually don't do it unless you give them a good argument. Yeah.
Any other question?
So we have submitted some proposals. Some of them were accepted. They are all either for, some of them were submitted in the last call before coming here. And no, we have pulsars, magnetars, and FRBs. But if you have a promising source, yeah, I mean, what do you have? The other problem is that the cycle, the proposal call is once a year and the next one is in next May. So.
Okay, so for the sake of time, please clap your hand for